And
I
that's,
want to take a break.
like, this just happened so fast, right?
All right, so right before the break, I think we discovered that this test statistic is wrong.
Right.
We decide that? This is not 20.884, this is instead
13,
13 and change.
13 point change.
618.
Alright, so these numbers are different, so if you're watching this at home, they're different.
Oh no, the numbers are correct, Professor.
Oh, the numbers are
Those
correct.
good.
They
It's
were-
just the total
My math was
wasn't.
bad.
They
There's
were
numbers,
summed incorrectly.
the numbers were correct, they were added up incorrectly.
Well, you can always play back.
Alright.
So you're watching this at home.
So that is our chi-squared test for proportion differences. We also know the chi-squared test for independence. Good news is that is calculated the exact same way. It's just a matter of how we interpret it. Our null hypothesis for chi-squared test for independence is these factors are independent. So your amount of study time and your statistics grade are independent. That means they have nothing to do with each other. That would be your null hypothesis. If that is true, you would expect certain numbers on grades. If you find deviance from those numbers, and there are large deviance from the numbers you would expect, you would reject this null hypothesis and say the factors are not independent. In fact, study time and grade are dependent factors. Grade is dependent on the amount of study time. Summary is the same thing. Show the observed frequencies, build a table of expected frequencies, compute the chi-squared test statistic, apply the appropriate decision rule. Alright, this chi-squared test statistic is what you calculate and add up based on that quantified difference between observed and expected. If that is greater than that critical value, that cutoff point for what you would believe, reject. You could also use the p-value version. P-value is the probability of that sample outcome if the null hypothesis is true. If that probability is really, really small, reject the null hypothesis. We of course know the degrees of freedom based on how many rows and how many columns. If we have lots of categories, we expect more difference. So we use degrees of freedom, and they're quantified in the back of your book with the table this way. Okay, so example of a test for independence. Speaking of statistics grades, we've got some data about statistics students at Bandon University over the past 5 years. A total of 1,000 students. They tracked how many times the students missed class and the grade that they got. The students were categorized in missing 3 or fewer classes, or missing 4 or more classes. So these are the students who came to class most of the time. These are the students who missed class a lot. And this is the grade that they got. Now, first thing I want to draw your attention to are the totals. Total number of students who came to class most of the time, total number of students who missed lots of classes. So we have fewer students who came to class most of the time. Alright, only 460 compared to most students. The majority of students missed lots of classes. Maybe this is a party school, nobody comes to class.
Howard?
Maybe this is a sports school, everybody's traveling and they missed for certain events, so a lot of students didn't come to class. The reason I point that out is look at the category of students who got A's. 160 for this category, 180 for this category. What is that? How do I interpret that? Just initially looking at it. Just tell me what's going on there. Which one is bigger?
180.
What's that?
180.
Okay, which group is bigger?
The one with the class.
Yeah, so do we have more, in the people who got A's, The bigger part was the people who missed more classes. Alright, but that doesn't necessarily prove anything because the whole percentage, the whole pie of students who missed lots of classes was bigger to begin with. So most of the students missed class. So just because we have more students here who got A's, that doesn't prove anything yet. We need to calculate the actual expected frequencies based on the total pie in each of these categories. And then we see the difference. That's what's going to matter to us with the chi-squared test. So let's now calculate. We'll just do one. Let's calculate the expected frequency here. Students who came to class, 160 of them got A's. How many would we expect in this cell? Okay, 156? Alright, so 156.4. Alright, good. So let's remind everyone, what is the null hypothesis for a chi-squared test for independence?
Population proportion, more than equal population.
No. Test for independence. Chi-squared test for independence. What's the null hypothesis?
Oh, that they're all independent.
Yes. So variables are independent. All right. And the alternative hypothesis is what? Yep. Variables are dependent. Okay. All right, and let's just say our significance level is 5%. Okay. So if we are to assume that variables are independent, this means what? How do you phrase that? In this particular case, what does this mean that the variables are independent? Yeah, that's right. Grades are independent of attendance. Another way of saying that is?
How often you attend class doesn't affect your grades.
Yeah, doesn't matter if you come to class.
Not for this one.
Alright, variables are independent. Another way of saying that, doesn't matter if you come to class.
You have to come here.
It will not have an effect on your grade. So if this is true, how many students who came to class most of the time would we expect to have gotten A's? 156.4. If this is true, we would expect 156.4 students to get A's. How many A's did we observe in that group?
160.
160. Okay, so what does that tell you? In terms of, do we have evidence that this is true or not true? Is this evidence counter to our null hypothesis? Does it support the null hypothesis?
Don't have enough evidence.
We don't have enough evidence, you're absolutely right, but what is just,
The numbers are different.
if numbers are different, what does it lean towards as of now?
But that's not true.
That we're rejecting.
That you're rejecting, okay? That you're gonna reject this null hypothesis. Because you would expect 156.4 students to get A's, but you actually see more. more students than you would expect got A's. Why do you think that was?
More geniuses.
New York classes.
We don't have any information about their IQ,
They had tutoring.
because they intended more class. Right, so that's not overwhelming evidence yet, but that's evidence in the direction that it does matter if you come to class, because we'd expect 156.4, but we saw more A's in students that come to class.
They got a good professor that gave them the answers.
Yes.
Is that a good thing?
Alright, let's do the expected frequency for this cell. How many of the students who did not come to class, how many A's would we expect? 186? 183.6. Okay, so, alright, that's not overwhelming evidence by any means yet, but what does it lean towards? What does it kind of start to indicate?
That it doesn't matter if you
Doesn't matter if you come to class?
that it doesn't,
That it does matter?
that it doesn't.
Okay, so you see this as evidence that it doesn't matter if you come to class?
It does matter.
I don't think so, you have to come first.
It does matter.
You gotta read it out.
Darling?
It does because we expect 183, we need 4, and we see 180. So we see that not as much A's for that group.
Yes, we see not as many A's as we would expect. And expect under what assumption? Under what assumption do we expect 183.6 A's?
Going to class or not, doesn't matter.
Independent. So under the doesn't matter if you come to class null hypothesis, we expect 183.6. But in this group, we see fewer. We see fewer than we would expect if this is true. What might explain why we see fewer than we would expect?
They didn't go to class.
They didn't go to class. So this is a little bit of evidence that this is not true. Not overwhelming evidence, but it's a little bit of evidence that this is not true. We okay there? Alright, so we've seen a little bit of evidence that this null hypothesis is not true. Let's just go ahead and crank this whole thing out. If we were to get the expected frequency for all 8 cells, that's what they would be. Alright, let's compare expected to observed, and let's do a chi-square test statistic, which takes the difference between expected and observed squared divided by expected for all 8 cells, and then sums them together. Alright, what do we get for our chi-square test statistic?
1.022.
Was 1 point what?
022.
022, okay. Alright, what is our chi-square critical value?
7.8.
Alright, so critical value, we need rows minus 1 times columns minus 1 for degrees of freedom. We look in the back of the book, 5%. 7.814?
1.5.
15? Okay. 5, alright, let's put this on a chi-square frequency distribution. Alright, this is 0 variation. That would be weird. We'd expect some variation if the null hypothesis is true. But too much variation, this would be our rejection region, which would contain 5% of the possible outcomes. And what number goes right here for the chi-square value? What number's right here? Yeah, 7.815. And where's our test statistic?
1.34.
Yes, right here. Alright, chi-square stat equals 1.022. What is our decision?
Fail to reject.
Fail to reject. What is the null hypothesis that we are failing to reject? The variables are independent. Another way of saying that,
Doesn't matter if you vote.
We do not have correlating events.
doesn't matter if you come to class. So in this obviously fabricated example, for entertainment purposes only, we are failing to reject the doesn't matter if you come to class null hypothesis. So this may be true. So, maybe, I don't know, maybe they have a good tutoring system. Yeah. Maybe they all pass around the answers
Yeah.
when they're away at their, basketball games. Who knows?
Maybe the professor takes all the classes.
Professor tapes all the classes, yes, that might be it. All right, good, any questions about that? What I wanted to show you last is how I recommend we do these on Excel. Let's take a look at page, I wanted to do, yeah, I wanted to do page 542, number 36. Take a look at that one.
For us, and then we'll create a marketing campaign based on those numbers. I just think that, let's compartmentalize where we're gonna. I like pictures. I can do reviews. We can be familiar with it as long as they don't want us to be, for that to be like a linchpin in the cornerstone of what we do.
Alright, let's just go ahead and start working through this. We've got a campus-wide survey asking students, do you plan to devote at least 1 year of your life to public service? Here are the responses. The freshmen, 68 of the total 130 said yes, 51 of sophomores said yes, 52 of juniors said yes, 59 of seniors said yes. Now note the totals, these are not equal totals in each. So kind of at first glance it looks like you've got a bunch of idealistic freshmen, and they get a little cynical sophomore, junior year, and then senior year they're like, okay, maybe, but that's just what it looks like unless you realize that it's out of a different total. Because they ask more freshmen, they ask fewer sophomores, fewer juniors. So we just need to quantify this with our chi-squared test statistic before we make any decisions about whether the response is independent of their class, their year. Do you understand what that means? So the null hypothesis is your opinion about public service has nothing to do with whether you're a freshman, sophomore, junior, senior. That's the null hypothesis. The alternative is no. It depends. If you're a freshman, you say yes. If you're a senior, you say no. So let's put all these in Excel. Alright, can you sort of see that? So I like to do 3 different tables. The first, observed. Alright, let's do class, freshman. If you want, you can do this along with me in Excel, or you can just watch. So freshman, soph, junior, senior, total. Alright, so let's say. Yes, this is no. So we got, So this is 68, 51, 52, 59, 62, 64, 58, 86. Okay, so that's the data. So I can make this, I don't need to look at the problem anymore. I can just make this bigger. And I'll see that, right?
Yes.
Alright, so let's get our totals. So let's do a sum function equals sum of all these. Boom. And this we can kind of, a variety of ways you can do this. You can just grab the corner of it and pull that formula over. Equals sum, open parenthesis, these two, boom. Same thing here, you can just grab the corner, pull that formula down. Let's do some formatting. Let's make these italics. Let's make these italics. Let's center them. Say, let's add some color. A little nice peach color here. Let's put some borders. Borders are always good to keep your thoughts straight. So all borders around everything, and then maybe a thick border on the outside. Yeah. Alright. Actually, let's center these too. And, let's just center everything. Every number. Okay. Alright. I'll put some color here. A little light gray and a little, let's see, nice little blue. Okay. Alright, so this is our observe. That's step 1. We've got our observed all in columns or cells. So we want to now calculate expected. So what I like to do is just copy this down here, Control V, paste, call this expected. Expected, boom. Alright, and then I'm going to another one. I'm going to actually add up the chi-square stat. Control V. Copy it again. Control copy. Control paste. Okay. So this formatting came out weird. Let's put that back to no color. And let's make it not italics and bold. Let's make all these bold. Bold. Should have been bold. No color, not italics, bold. Alright, so this first thing we do is we erase these expected, because those are not expected. And these totals, we don't need these totals, so just delete those. Delete those. Same thing here for the chi-square stat. We want to put in different numbers. Okay, so I'll make this a little smaller so you can see both. Alright, so I want my expected number of freshmen who said yes to go in this cell. So remember, column total divided by grand total times row total. So this equals column total divided by grand total times row total. Hit return. Boom. You like it?
Yes.
59.8. Now, do you all know about that absolute reference, the F4 $ thing? So what I could do is I could just do this again 8 times if I wanted to. In fact, I'll do it 1 time here. So equals, I'll just do a random one. I'll do this one right here. Alright, so this equals the row total divided by grand total times, for that particular one, junior, by row total. So column total divided by grand total times row total. Boom. Alright, so I could do that 8 times. I could also put absolute references in here. So what an absolute reference is, you see this E8, the grand total? I don't want that to change. In any of these 8 calculations, it's always going to be referencing row E8. So what I can do is I can put $sign in front of E, and I can put $sign in front of 8. Okay, so that cell will always change if I will always stay the same if I copy and paste this formula. For the C8 here, all right, it's referencing the column total. I want the 8, I want that to stay the same, but sometimes I want it to be the D, sometimes I want it to be C. So I want the 8 to be the same always, but I want it to let the C change. So I'm going to put a $sign in front of the 8, because I don't want that to ever change. It's always going to be row 8, but it could switch to column C or D. And lastly, this E4 that it's referencing, this is the row total. I want that to always be column E, but I want it to switch rows as necessary. So I'm going to put a $sign in front of E, and I'm going to hit return. So now I have absolute references, and I can just copy and paste this formula 8 times. So I can just pull this down, boom. Alright, for this one, I can just pull this over, boom. Alright, now remember that's 59.4, so hopefully it stays 59.4 when I copy and paste that a formula that had absolute references in it. So 59.4, yes! It worked, right?
Boom. That again.
So, yeah, don't worry about the $signs. Just do row total, column total divided by grand total times row total. Do that 8 times. Column total divided by grand total. Remember how I did it for this one and then I did it for this one? I did it twice. You just do it 8 times.
Can you go over the $sign?
Yeah, that was like too fast.
Fix the cell, to fix the
I lost
cell.
all the dollar signs. No, but that's good for me to learn to work.
Okay,
So over that.
okay, sure.
The dollar signs.
Yeah. Yeah, a column total divided by grand total times row total. Okay, so I could do this 8 times, or I could just do absolute references. And what I just went over is a way to just make your life a little easier by doing absolute references. So for each of these 8 cells, all of them are going to be, this is going to be the grand total. The grand total is going to be the same for all these 8 cells. So I can copy this formula, and if I put it in these 8 cells, this E4, or excuse me, this E8, the grand total, is always going to be the same. So what I did is I put $signs in, so it wouldn't change as I copied and pasted that formula. If I didn't put those dollar signs in, then it would just move down, like the second one would try to find the grand total here, the next row down would try to find the grand total here. And when I went over to the nose, it would try to find the grand total here. And that's not what you want. You want it to hard code in an absolute reference, this is a grand total. So what I did, saves you a little bit of time, is put the dollar signs before the E and the A's. And we did roughly the same thing with the column total and the row total, except we said for the column total, which was 230 in this case, I want this to always reference the eighth row. But I want, sometimes the column total is gonna be in C, sometimes it's gonna be in D. So I let that C and D be relative, but I want the 8 to be absolute. And then the same type of thing for the E, for the E4, for the row total.
Dollar sign for the.
Yeah, we're actually gonna have to move on because this is an advanced move, and I don't wanna confuse anyone
Could you
any more
just
than that.
zoom in on your formula line for 1 second? The top formula line, right, that's fine.
Alright, yeah, you're gonna have to look at this later.
Okay.
Okay, so what's our next step?
Now you're gonna take the differences between the two columns.
Yep.
And you're gonna square it and
Difference is
divide it
squared
by
divided by
the expected.
expected. Okay, so for this first one, this equals open parenthesis, it's observed minus expected, right? Observed minus expected, close parenthesis, square that, and divide by expected, right? Return. Wait, what did I do wrong? Yes. Equals, I did something wrong, sorry. Observed minus expected, close parentheses. Let's square that.
What's the symbol to square?
It's 6, shift 6, divided by expected. Oh, there we go. Okay. Now, this one, I want to actually, I can just copy and paste this cell, because I can copy this and paste it in this cell, because what it's gonna do, it's just gonna move down 1 notch here, it's gonna move down 1 notch here. And if I copy and paste this and put it over here, it's just gonna move everything over 1 notch here and 1 notch here. So this, I don't need to do that hard coding. I just copy and paste this formula here, boom. Copy and paste this formula here, boom. Copy and paste the formula down there. Alright, and I want the total, remember how we divided up and sorry, can't see that. I want the total, remember how we divided up and some of you worked on each cell and we added them all together?
Yep.
So we want the total equals sum of all of those. Boom. So this 3.966, what's the term for that? What do we call that?
Test that.
The chi-squared stat. Yes, absolutely. The chi-squared test statistic. So, the question is that bigger than the critical value? And what do we say if it's bigger than the critical value? Reject. Is it smaller than the critical value? There's less variation between what we observed and what we expect if the null hypothesis is true. Then we fail to reject. so let's put that up on the board. So the null and alternative hypotheses are here, actually the same thing, same from the last problem. Everything's the same, wow, check that out. Easy, right? Okay, so our chi-square test statistic is 3.96635, thank you.
Numbers are different.
All right. What is the critical value?
Seven point eight one five.
Look,
7.815, you like that? Degrees of freedom, rows minus 1 times columns minus 1. Look in the back of the book, whatever degrees of freedom that is. 5%, a whole 5% is in the right tail. Alright, so we've got 7.815. Our test statistic is 3.96 and change. What is our decision?
Fail to reject.
Fail to reject. We are failing to reject that the variables are independent. What does variables are independent mean in this case?
Your response has nothing to do with what class you're in.
Yes, your response has nothing to do with what class you're in. You might be tempted to say the freshmen are all idealistic and they're going to go into public service, the seniors are more cynical, whatever. You get cynical in your sophomore, junior year, and then you change your mind. We don't have any evidence of any of that.
When they realize that they owe too much money and they have to make more money.
Yeah, well, we don't have any evidence of that. We don't have any evidence that their opinion changes as they go from freshman, sophomore, junior, senior year. It could be that they are completely independent. Response doesn't matter. Is there a question? Yes, Ron.
So when we did z-scores and t-stat, and we looked at critical values, we were looking at standard deviations, right? Here we're not. When we looked at critical values,
Critical values, we were looking, yeah, we were. For z-scores, we were looking
but this obviously isn't because of,
something like standard
it
deviations.
is, okay.
Yeah,
The number's
just-
so high though.
Yeah, just like you mentioned, or you asked earlier, is it based on sampling distribution and sample mean stuff? Yeah, it's the same thing underlying it, but it just gets complicated. Rows, categories, how do you quantify it? Well, the statisticians figured this out for us, but it's the same thing. It's some number of standard deviations. This, we would expect the difference to be some certain number of standard deviations away from 0, but it's so many more standard deviations away from 0 that it's highly unusual, but it's the exact same thing. Alright, so
Can you show the formula? Can you just put that in the bar? The formula you use for the chi-square stats.
for this, okay, yeah. So this is just observed minus expected. I guess you can't really see it. Sorry, I don't know. This is
We got different numbers, that's why.
this is right. I remember it from last night. We can check the back of the book just to be sure, but this is correct.
Isn't it, it's observed minus expected squared divided by expected? Don't you have to do double parentheses, or no?
Double what?
Parentheses. For the,
No, you can do, because the only thing you need to do the
expected numbers
parentheses
are
for is to make sure you do the minus first. So once you do the minus, then Excel will automatically do the squared next. It doesn't matter if you do the squared. Except, I guess Excel will automatically do the squared first, because you need to do the squared first. But I guess Excel automatically does it for you. You could do double parentheses.
no, I
Just be
did it,
safe.
and it got it, it gave me a different number.
Yeah, I did it too, and it gave me a
It gave
different
me
number.
1.1 something, so.
You
I got
divide by
1.12.
observed by accident.
I got one, yeah,
I
one.
think you divide by
One point
D4.
one two.
I did?
That's what I
Yeah,
did.
D6, divided by D6.
Yeah, I came up with different numbers.
We all have the same one.
I think the chi-square stat is 3.93.
It's a good thing we didn't get this on tape.
It's not.
Aren't you recording? You're not recording?
Yes.
So this is different than the number in the back of the book.
3.93 in the back?
I got 3.9. I got 1.1 something.
Yeah, 3.93 I got.
Nice. Okay, sorry about that. So this is, actually we can do the click here.
Rewind.
So this is, whatever, I'll just do it again. Equals, parentheses, so it's observed minus expected squared divided by expected, right?
You didn't square it.
You have to square 2. You have to put a 2 there.
Yeah, oh yeah, put a square there, okay. So squared divided by expected, okay.
What do you have? That's it.
Yeah,
That's correct.
Okay, now.
So what is it, 1.12?
Yeah.
Oh, it's still. Can't believe it. I can't, oh, you're right. So how do you fix something?
Okay, why is that?
How do you fix the number?
Yep, that's what I have.
Okay, sorry about that. So this matches the textbook. Okay. So be careful with your cell references. So this is 3.926. 3.926. All right. Well, so yeah, this is the way I would suggest you do it on Excel, and you should practice doing that a couple of times. And you can answer the quiz questions with the table just like this. I believe there are 2 chi-square tests on your quiz, one proportion difference, the other test for independence. Of course, they're calculated the exact same way. The final exam will be one of those questions with different numbers. Now the final exam also might have a different number of categories, so you need to be aware of that. Be prepared for that. It'll be the same thing, just with a few differences. Any questions? All right, you all have been fantastic. Enjoyed working with you. Please stay in touch. Let me know if I can. Let me know if I can help with anything.
Is that
This is the last class?
This is the last class.
Is it?
It's almost, I guess you're giving us next class to just complete our final at home.
We don't have to come in to take the
Finals online.
Finals
Finals online. Starting Sunday, completed by Wednesday.
Yeah, you were great.
It was so clear, because we couldn't retain.
Oh, it's-